In this video, we're going to look at how to use Monte Carlo simulation as a numerical integration method. So let's think about having an arbitrary function g. So here's x and g of x, and we don't know what this function looks like, maybe something like that. And our interest here is in finding the integral on a definite interval. So I've got my interval here, a, let's say there's a, and there's b. And what I'd like to find is I is equal to the integral from a to b gx dx. And let's assume that the integral is such that I can't solve. So I can't solve this analytically. And so a very standard numerical method for doing this integration is to divide the range space up into n equally spaced intervals. So I'm just going to divide this up as follows, and I'm dividing into n intervals. And then if I do that, I can estimate I, say I hat, is simply equal to b minus a times the average gxi, where my xi is one of my interval boundaries. So in other words, what I'm doing is each gxi is simply the, if you think about it in 2 dimensions anyway, the height at my value xi, and so I'm solving for each of these individual little rectangles, or I could do trapezoids also. And as I increase n, so if I went from this layout interval size to say doubling the number n, or having the size of the interval, I'm going to get a better and better estimate. So I'm making these individual intervals smaller and smaller and smaller. The Monte Carlo method says what I want to do is let's assume that this, instead of being on equally spaced intervals, is uniformly distributed on the interval a to b. So instead of dividing my interval ab into equally spaced intervals, I'm going to just randomly choose one. I'm just going to randomly choose a location. And so in essence, when we do this, we're defining a new random variable, y, which is simply equal to b minus a times g of xi, where my xi is uniformly distributed on the interval ab. And so when I do that, my expected value of my new random variable I is simply equal to 1 over n times the summation b minus a gxi. And of course we can pull the b minus a out, and we get our b minus a over n summation gxi. So in essence the same representation that we had above. The only difference now is that our xi's are going to be sampled using this uniform distribution on the interval. So let's see how we can code this in using a Monte Carlo simulation. So let me clear that. And what we need to do, if we're going to do this programmatically, is the follows. Let's just define a variable total and set it equal to 0. And then we're going to loop through some number of iterations. So for I equals 1, 2 iterations, what do we need to do? Well, we need to sample a UI which is uniform on AB, and then increment total plus g of UI. So whatever the function g is, I'm just going to apply that function to my sample and then exit my loop. And so I have now summed up all of my individual g of UI values. And so now our estimate, which I'm going to call I hat, is simply equal to b minus a divided by n times total. And so this simple pseudocode gives me the logic for doing a Monte Carlo simulation. And of course what we need to specify here, we need to specify the number of iterations. we need to specify a, we need to specify b, and we need to have access to this function g. So clearly the more iterations we do, the better our estimate is going to be of I hat. And so if you're interested, here's some Perl code that actually does this Monte Carlo integration. Let's see what I have here for my value. And so you can see that I've used lower and upper to represent A and B. I have the mean and standard deviation that's part of my G function down here. And then I define a constant part of f. Looks like I'm doing the normal distribution here. So there's a constant part of my function. I do 10,000 replications, and then I have just a Boolean variable to tell whether you're going to show intermediate results. And so here's the main loop that I have. So in my pseudocode, you can see that I sampled my UI and then I incremented total. And in this case, I just created a separate evaluate function. So I just add to my total sum the response from the evaluate function. And in evaluate, I sample a U01. That's what this function does. And then I print it if you want to see it. Then I convert that into a uniform AB by lower plus U times the range. And then here's where I apply my what I call G in the previous in the handwritten slides function here. And so I just take the constant part and then the expose. So again, this looks like the normal distribution, and then return the value. So you can see that the code here, my Perl code, just implements this same logic. It just does it just slightly differently by creating this evaluate function. So at this point, one natural question would be, why would I want to use this Monte Carlo method, say, versus the method where I divide up into equally spaced intervals? And the actual answer to that question is the subject for another video. It's fairly detailed, but the short answer is that in general, we can get a better error bound using the Monte Carlo method, particularly when we're talking about multi-dimensional random variables. So we just took a nice single-dimension random variable and divided it up into equal space intervals. But if you think about a two-dimensional, you're going to have equally spaced surfaces, and if you have a three-dimensional random variable, 4, 5, and 6. And so as you increase the dimension of the random variable, you're significantly increasing the number of these little portions you have to have when you divide it up. And so as I said, it turns out that using Monte Carlo simulation, you can get a better error bound. So in either method, whether we do the interval method or the Monte Carlo method, we're estimating. And so we know we have error induced by that estimation. And so the Monte Carlo method can give you a better bound on that error. But as I said, that's a topic of another video where we would go through some amount of detail.